You've probably used one of these before, right? An instant cold pack. It feels like a little piece of everyday magic, this chemical puzzle you can just hold right in your hands. But how does it actually work? I mean, really think about it for a second. You squeeze it, you shake it up a bit, and all of a sudden it's freezing cold. There's no ice, there's no electricity, no freezer involved. So what is the secret? Well, it all comes down to a really fascinating chemical process. So let's do it. Let's crack the code behind this amazing spontaneous cooling. And to do that, we first need to get our heads around one key scientific term. And that term is endothermic. Now I know it sounds a little technical, but if you break it down, it's actually super simple. Endo literally just means inside, and thermic, well, that means heat. So an endothermic reaction is just a reaction that pulls heat inside itself. It sucks it in from its surroundings. And here is the absolute key. If a reaction is pulling heat away from its environment, then that environment has to get colder, right? The cold pack isn't creating cold out of thin air. No, it's actively absorbing heat from everything it touches, including you. What you're feeling as cold is really just the absence of heat, as your own body heat is being drawn straight into that pack. But to really get why it absorbs all that heat, we've got to zoom in, way in. See, at the molecular level, every single chemical reaction is kind of like an uphill energy battle. It's all about breaking old bonds and making new ones. Okay, so every chemical reaction you can think of has these two basic steps. First, you have to break the original chemical bonds apart, and that always takes energy. You got to put energy in. Think of it like trying to snap a twig. It takes some effort. Then, step 2, new bonds are formed, and this part of the process always releases energy. And this right here, this is the whole secret. In an endothermic reaction, the energy you need to break those old bonds is way more than the energy you get back from forming the new ones. So you've got this energy deficit, right? And the reaction has to get that extra energy from somewhere. And where does it get it? From its surroundings. You know, a really great way to picture this is to think about pushing a big, heavy ball up a hill. It's this constant uphill climb that needs you to keep putting energy into it just to make it happen. The reaction can't go on its own. It needs that constant energy boost from the outside world. And what's the result of all that effort? Because all that energy was pulled in from the outside, the final products, the new molecules, actually end up storing more energy in their bonds than the original ingredients even had to begin with. The heat from the environment is now basically lacked away as chemical energy. Pretty cool. Now, this isn't just some neat little trick for first aid kits. Oh no, endothermic processes are happening constantly all around us in some of the most important systems on our entire planet. So yeah, inside that cold pack, you've got water mixing with a salt, usually ammonium nitrate, and that's what triggers the reaction. But this process is everywhere. Photosynthesis, the foundation for almost all life on Earth, is just one giant endothermic reaction, using sunlight as its energy source. And hey, even something as simple as ice melting is endothermic. That ice cube has to pull heat from the air around it just to break its solid bonds and turn into liquid water. And to really make this idea stick, let's look at its total opposite. Exothermic reactions. It's simple. If endothermic feels cold, exothermic feels hot. Think of a campfire. It's not absorbing heat, it's releasing it, right? It's warming you up. It is the exact same principle, just with the energy flowing in the complete opposite direction, out of the system instead of into it. So let's talk about why all this matters. Because this isn't just some chemical curiosity you learn about in a classroom. It is absolutely essential for technology, for nature, and even for our planet's climate. So yeah, this goes way, way beyond a cold pack for a sprained ankle. This process is what fuels literally all plant life on Earth through photosynthesis. It drives enormous weather systems. I mean, every single time water evaporates from the ocean, that's an endothermic process absorbing the sun's heat. It's just fundamental to our world and to so many key industrial processes. There's a quote that just sums this all up so perfectly. We usually think of chemistry as things that get hot or bubble or even explode. But sometimes the most powerful reactions are the quiet ones, the ones that are defined not by the heat they create, but by the heat they take away. So let's circle all the way back to our original mystery. Why does a cold pack get cold? Well, now you know. It's because when you mix those chemicals inside, you trigger an endothermic reaction, one that's just hungry for energy. It pulls heat from everything it can touch, the pack itself, the air, and your skin, leaving nothing but that sensation of cold behind. So it's not magic, it's just very, very cool chemistry.